All right, let's begin. Welcome back to the stream. Welcome back to the video. Welcome back to our channel from Breadboard to Marketplace. If you're enjoying us, enjoying what we're doing, enjoying this series, definitely like and subscribe. Hit that bell notification to be informed of any videos that are uploaded to YouTube. I'm trying to get everything uploaded as soon as possible for this exciting series because I know how eager everybody is to watch it, especially if you've stuck with the series up to this video. So the last video, we were writing our test plan. Started kind of poking around a little bit to some of the individual firmware modules that we want to test the individual sections, such as the UART, the LED and stuff. Ran into a little bit of a wall, so we ended up writing some of the other kind of preliminary test plans for some of the other functionality blocks that we want to test. So I did some digging, and it was because the ESP-IDF did update to version 6, and I did some research, and it looks like they basically, all the peripheral drivers, they have new APIs for them. And so all the old peripheral drivers for like UART, I2C, SPI, and all that have been kind of redone and are now considered legacy. So I went back to the prior version, the 5.2 point something of the IDF, and everything works fine now. I was able to compile and flash my initial UART test. Right now, this is just basically a basic UART terminal. It hasn't been customized for this yet. So basically, all it does is, and then I can do. So I can do basic things like that through PuTTY or another terminal emulator. So I could leave this as this, and or we can just kind of like customize this module for this test for this device, which might not be a bad idea. So we can make it clear that it's a test. And what's cool is since this is a separate UART port, I don't have to worry about the COM shutting down or anything to flash or disconnecting, so I can update new firmware. So right here in the main loop, the main app, this is where it calls the UART console C, which this is what does all the legwork, initiates, basically becomes a task. Yeah. So yeah, basically it kicks everything and then it kicks it off as a task in RTOS. I don't have any priority interrupting or anything on this, but it is a separate task for RTOS to handle. So right here, we're basically just using the built-in tokenizer in C. Where basically it's a two-part argument, or a two-part command and argument delimited with a space, as we put here. So that's actually a space, just to make sure. Just so it's clear, you can use any delimiter you want. You can use a pipe if you really wanted to, if you want to make it clear. But most of us naturally will use a space between a command and an argument. So you want to keep things short and sweet. So it takes that, tokenizes it to a command and an argument. It parses it, and then. So yeah, it parses the input and all this stuff, and up here. So what we will do is, so this is like if you hit the melt command. So what we can do is after we initialize, we can even do it here. So this is cool right here. This little bit of line of code. I looked that up, but that is a command line, a command argument that will actually clear the console screen, at least for PuTTY that I know of. And I think I've got the command here. So basically we parse, you know, if the command is this is what it does. If it's clear, this is what it does. So you kind of have to break all this down. So if we go to putty right here, and I just type clear, clears the console. Actually, it's pretty cool, pretty fun. So what I'm going to do is come here. Let's do that. So let's what we're going to do is we're just going to send a custom message for this project. All right, 101, 101, 22, 0, 25, 01, 1, UART, FTDI, test firmware. So that way, when when the device loads up, so let us build project. It should actually successfully build because it did the other day. And it shouldn't have to be rebuilt. I'm not going to do a clean and rebuild because we're just kind of updating existing files. And I have the git ignore file for the root of the project for all the documentation and all these files, so it should ignore the build folder. I pushed it up already this morning for the changes, or earlier today for the changes from the last stream. I updated the git ignore, and it does look like it ignored the build directory, so shouldn't have to worry about that bogging down any downloads. So let's go and flash it. Pull up this guy while we wait. So now when it reboots, there we go. Your FTDI interface has firmware. Perfect. And then, you know, if you reset the device, reset the device. I don't know why. Oh, because it happened so fast. It's clearing it and it's bringing it right back up. So if we do that and we reset. So yeah. So that way when the device powers up or you reset it, you're presented with, you know, basically a message, because that's what this is. It's an FTDI interface test firmware. So we're going to go ahead and come over to here. So see if I can copy and paste this into here. Test plan. So FTDI on reset or after and button. Message should appear on the terminal. Here we go. All right. Okay. So we're updating the SST. Load up putty with the settings. These port. COM port baud rate of 100. So if we go to PuTTY, settings, it is serial. 8 data bits, 1 stop. And no parity. Get rid of this line. Let's press firmware. That should pop up as it does here. So we will have that. So mind you, it's going to say that, but if I hit enable or reset, it's going to send a clear terminal screen and just show up that, present that. So now we want to kind of just to clean this up. We don't really need help, but we'll leave it. We'll leave clear, echo. No, actually, we'll just leave it alone. In the terminal. So let's go here. Type in following echo test. Don't really need the period there. So if we go here, so what this is testing is bidirectional communication, and that the UART interface, the serial console, is actually receiving data. It's clean data, and it's actually parsing it properly, and it's functional. Echo test should receive a response sent back that looks like following. Not as clean to organize as like a Word or a LibreOffice file would be for this, but I think it presents just enough. It should be fine for what we're trying to do. Echo test. This one should be sent back. Looks like the following. Echo test. If successful, this is a condition. All right. So that is pretty cool. So we have actually verified that that works, at least on this dev kit. So at least on this dev kit that has the same ESP32, it flashes, and the USB or the FTDI UART interface does work. And again, we'll test it. This will be tested on the actual built PCB, which hopefully be sometime next week. Maybe it depends when the boards come in. I might try pushing it to the weekend, so I have like next Saturday or next Sunday to actually take the time, maybe make a longer video of building the boards. Who knows? We'll see how that goes. Even if we do receive the PCBs and the stencils in on Monday, because there's still some testing documentation I'd like to make sure we have ready to go for this. Plus, I want to make sure the workstation I have in the workshop is set up properly for recording all the test documentation, and has LibreOffice installed. Everything's updated so we can run the testing firmware and stuff. Okay, and organize a few things so it'd be easier to have the camera watch, for the build process stuff. I got some other stuff coming from Amazon to help set that up better, ring light and stuff like that. So hopefully that'll all come in before I have to even worry about checking in the PCBs. Maybe we can do a little bit better lighting and I can get things better organized. But so this works. All this will be uploaded to the GitHub. The UART console, I've just got the README MD file in there. Basically kind of breaks things down. I put in there, don't go with version 6 because they updated the drivers for newer APIs, and I rather wait for a couple of releases, a couple other versioning, to take the time to rewrite in case they have to fix anything or there's any addendums to the drivers. That way they can work on any kinks before I take the time to write for the new APIs. Right now, the legacy version that we're using now, it works and it doesn't look like it's going to be depreciated that fast. So we have some time. As long as we still can get the older IDF version, we'll stick with it for now. There's no reason not to. But all this, it's basically an open license, the UART console. So it should have a good breakdown on how to use it. If it, this main file from here will be there. So you can use these for examples to incorporate into your own firmware if you want. No big deal. Again, this is just a basic UART console that tokenizes the command and arguments. And you can add multiple arguments just by building out on the tokenizer. So that's the process command. So here's the parse input. This is what tokenizes it. So you can keep adding more tokens, basically. So right here would be print Fs. Yeah. So this would be the command, your argument. So you just keep building on this and just add more arguments. But typically one argument's more than enough, depending on how it's written. As long as you can basically kind of parse it up here into basically easy to digest ASCII text string, basically. So that should take care of this guy. Everything should be saved. It just likes to flag because spelling errors, and it says it can't find this, but it's there. I don't know why the ESP-IDF does that. The free RTOS is there. I don't think I need it in the main file, but I just leave this stuff here. It's not going to hurt anything. That is the UART interface. So we don't need the PuTTY interface anymore. Get rid of that guy. So that takes care of that. Now I have an RS-45 breakout board that I can interface with the ESP32 dev kit. I have to find it. I've been organizing my workshop in my office, and things are just helter-skelter everywhere. So I know I've got a couple of RS-45 breakout boards. And we can test that. Maybe write a test for that. Maybe tomorrow or Sunday, depending when I find it. I just got to do some cleaning and organizing. So what we can do is maybe kind of look at this. I don't mind. I kind of would rather just write these tests away from the camera so I don't bore anybody, because again, I'm not much of a coder, so I have to look a lot of stuff up to remember it. So it might be easier if I get the tests written, and some of them you won't really be able to see without a camera monitoring the PCB, at least the dev kit here. So maybe we'll get some stuff set up, and maybe I can use a camera once I get that, at least until we get the PCB built. But for now, we can continue sussing this out, because one of the things I also wanted to do was the input test. So this tests the limit switches and the inputs using the commons all tied to ground. So that would be if you were basically taking 24 volts off of the power supply that feeds this. 24 volts, imagine it right here, comes out into a switch, from that switch or button into here, and then it comes in here through that resistor, through this opto isolator, through the LED side of it, the AC LED side of it, and comes out through the common, hits this common, and goes to ground to complete the path. And that would trigger this optocoupler. So that's what that test is for, like basically an internal supply. So the next test I want to kind of suss out is SST 12. Starting here, we would keep the, I better fix it. I don't know why I don't just hit home and fix it. Old habits never die. SST 12. With the input test firmware flashed to the so another term that they'll call these kind of things, these devices, that like I'm calling it a PCB assembly, but you also hear DUT being used, which stands for device under test. So you'll see this, used formally a lot, DUT, device under test. You could use whatever as long as, it's clear enough to convey what you're trying to do. To the PCB assembly, it's still acceptable. So just in case you ever hear DUT or device under test, that's pretty much what it means, the device you're testing. Device under test is probably more appropriate, but who cares? The message gets across. Firmware flash to the PCB assembly. Remove the jumpers on J2 and J3. Remove the jumpers on J2 and J3. That is important because we don't want this common tied to ground anymore. We don't want it using the ground inside the system, because this is going to be basically PLC testing. I'm going to have to suss out some of the rest of the details in here and get like models and stuff and come up with a name for it. So let's see, let's go into the folder here, basic modules, firmware. So, I don't need that. I'm going to create a new folder here. Let's see. Additional testing. Don't know what to call it because there could be additional testing or additional modules. So I'm just going to throw in here PLC. So I'm going to be using a click to PLC click or click PLC to test this with, because the one that I have has a discrete input output module on it. So it has, if I remember right, 8 inputs and 6 outputs. And funny enough, the 6 outputs are the exact number that we need to do testing with this. So I'm going to be writing a PLC program to handle the testing. And the great thing about the clicks is the software is free. The picks are low cost. So if you wanted to get into it, you can get basically what I would say an entry level pick with a module for around, they're low cost compared relative to, like, you know, Rockwell, you know, Allen Bradley, the big companies, Siemens, Koyo, I think it is. They're relatively inexpensive when you compare them to those market dominators. But, you know, it's relative, like I said, so about $450. You can get the PLC, a good PLC with the discrete GPIO interface module for it, which isn't bad. And again, the software's free. So that's what makes it easy. So since it's free, I'm going to be writing the PLC program. I'll throw it in here. It'll be part of things you can download and play around with. So here, I haven't gotten a name, you know, since I don't have the Click PLC software in front of me. We're just going to kind of name it. And I got to get all the details for the Click and stuff for the PLC we're going to be using, but we're just going to kind of throw in some placeholders for now. So let's see here. Okay. So one of the things I want to do before I forget, let's get through all this mess up here. Oh, look at that. We already kind of covered. Okay. So I will also lay out a few things here. So with the input test firmware flash, move the jumpers on J2 and J, that is important. Okay. Okay, so I'll disconnect any wires tied to CN 3 or 4, CN 4. Okay, so I'm going to pre-wire basically a test setup for this. Basically, since I got the pluggables, I'm going to pre-wire it and kind of, you know, I'll show it to you, but right now I'm just kind of describe what we're going to do here. So let's see, install. So now we're going to connect the test button to the PLC by test button number 1 wire, the PLC power supply positive terminal block. So the inputs are syncing, basically. The inputs and outputs are syncing on this. So they have a common, typically, which goes to your negative. And then you basically would pass a positive 24 volts into each of these inputs through like a switch or a button, and it would activate that input. So essentially, if you don't know if you've caught this in the last video, so essentially the PLC inputs and even their outputs are basically just these opto isolator circuits. So the input, so an input is basically, you know, the anode cathode side of the LED. And then if you're using it for an output, you know, so an input, it would use basically the circuit to go to its microcontroller to handle, oh, I've got an input. But if you're using it as an output, essentially your microcontroller sends a signal on this side, and then you have your positive side, and then it comes through, and then it, you know, basically syncs it to ground. So it's basically a low side switch, if I'm not mistaken. So it's a syncing input or syncing output. So imagine a relay, a contactless relay is basically how it's working. So positive terminal block. So we have to do that. Connect the number 2 wire, the PLC X1 terminal. So for those who don't really work with too many PLCs or anything, and I may be completely wrong on this, but it's been across this way for as long as I remember working with my exposure to them. So X insert number or inputs, and Y's are outputs, and then there's other special letter designators for other internal functions to the PLC. But in this case, anything labeled with an X is an input and a Y is an output, which makes perfect sense. Act on X to get Y. And inside through the ladder logic, you can have, an X1 input activate Y5 output. It's all how you program it. So the number 2 wire, so basically this will create the connection to the PLC input side. So that's going to be the test button. They're basically the same test button that we used for the input test. I might have to just kind of give it a name, maybe even kind of build one and give it a part number. Design like a 3D printed enclosure. Maybe I'll work on that over the weekend too, and take pictures or show it on the video. We'll do something cool and fancy, because it can also be for a longer term test fixture that we can work with. We'll see. We'll see on that one. Okay, so that's the X1 input terminal. Now, connect the PLC Y1. Okay. Connect the PCB assembly CN3 terminal 1. Don't need to capitalize that. Terminal 1 to the PLC Y1 output. The CN3 to Y2 output. The CN3 Y3 output. And four to the PLC also, if I spelled that right. Okay. So again, what that'll effectively do is tie this limit COM in here. So now the COM is going to become positive. That's why you don't want this ground connection here. You could fry something, or at least kick overcurrent protection on the power supply. So you want to disconnect that COM. So now this COM is positive. It'll go through. So let's just look at it this way. It'll come through here. Since this is an AC input, you can have your current flowing anyway. So coming through here, out through terminal 1, goes into the PLC's input, basically, and sync it to ground, completing the circuit. So that's basically what we'll be doing. It'll actually be going through 2 opto isolators. But it'll work just fine. Or it should work just fine, because I've kind of got like a middle of the road resistance here. It should be just fine, enough to trigger. I will probably do some additional testing on my own time to make sure, but it should work just fine. That's why I chose this resistance value. It's pretty middle of the road. Good brightness, so it shouldn't affect the other opto. Because remember, through an LED, you're going to have a voltage drop as well. So we may end up having to change this resistor down the road to allow more brightness, but you've got quite these things can go quite dim before they don't even respond. I've seen that firsthand, trying to diagnose some other things. So that should be fine for that. So what we've done with that is this. And now because this firmware, will be testing both of these inputs at the same time, now we got to do CN4. Connect. So I'll have a pre-wired headers for all this, or pluggables. So I won't have to do this on camera. It'll already be wired, but this tells you what you need to do. PCB assembly CN4. 1 to the PLC out. PLC Y4 output. The CN4 to PLC Y5 and 3 6 output. And the CN4 to the positive power supply. So for 12, it's a long-winded because once we get into the other, well, actually, 12 is long-winded because it's not written like I would like to break it down into different sections, but this is mainly just get the point across what you're supposed to do. Formatting and, you know, as long as you understand what you're supposed to do, that is the main objective with any of this. Formatting, making it look pretty, that's not necessarily a requirement of a QMS system. That's personal preference. It just has to be understandable, human readable. But to me, this is, again, I'll have other people read it. If we have to rewrite this, kind of break away and change how this is formatted, how it looks, that's fine. I don't mind. But for now, this is mainly just to outline and get the job done. So, once that is all done, nope. You see, not the PLC properly powered up properly because there are a couple of different inputs for these PLCs. So I'm gonna update the documentation here once I get some data or some details. Give you like maybe the model number. Click PLC with the testing program installed. PLC should have the I'm going to update this part number here. Okay. The reason I'm going to kind of put some more details up here is because you get a different PLCs powered from different sources. I think there's the one variant they have can be powered directly from AC mains. I prefer the ones that are powered from 24 volts from standard DC, just because I feel more comfortable, working around it. And I feel a little safer rather than working around mains. Even though I have a power supply set up, an AC/DC power supply, I still feel safer working with the DC side because I haven't been thrown across the room by a DC. So we're going to kind of get rid of that line because we don't need that anymore. Screen input out module install, because I'm going to put click PLC here with testing program. There we go. There we go. Properly verify the PLCs are powered up properly. Place the PLC into on mode. Take a few seconds. Settle. Press the test button and observe the PCB assembly LED D9. Okay. So basically what the LED should do, LED should follow a similar, I'm just kind of rating this now. I'll suss out the actual test program. And I have some stuff I can do more testing with on with the PLC and stuff on my own time to validate and write and and do some verification. I don't want to suss it all out because it's going to have a similar link as in tests, but in sequence. So, okay. So, yeah, so basically it'll go through, it'll kind of follow all these flashes. I'll kind of suss all that out and do some independent testing again and spell it out here in this section. It'll basically, flash once, delay like 2 seconds, flash, and then wait 2 seconds, flash twice, wait 2 seconds, flash 3 times, wait 2 seconds. So basically run through all these tests, but sequentially and on its own. It's going to be all automated. And mainly that is to test and validate that these input circuits do function properly with the common tied to positive and going through a PLC's output, basically. That way, if you wanted to use this device in a system that uses a PLC for input control or commands, and you wanted to write something like a Modbus protocol over RS-485, you can do that, and you can still control these inputs. Even though I call them limit switches, here, there's just GPIO. You can rewrite them to be whatever you want them to be. This is just for, separation and understanding how the core design principles. So that should test that. So let's update the test log. This is T12. Do the using a PLC as a control source. All right. So that basically covers that part of the testing. Let's copy this. Let's not make this too wordy. So, we'll worry about that last. Well, let's see what other subsystems we should be testing. So we have the USB UART. That's already been tested. ESP32. That's tested, but we'll be testing that LED. RS485, we're going to be sussing out a test for. Again, that's going to be based off of the existing UART test that we were playing around with. But if I remember right, the ESP32 has basically settings to directly control an RS485 chip. Basically, the direction basically sets the read enable, the drive enable, lower or high, so you can control your direction, your flow. So we have that covered of those. So the only last test that we need to really work on is the stepper motor. So let us go back over to here. Okay. Okay. Completed. To stop. I think it's stop. I'll double check mode and power down. The PLC for next. Here we go. Not fancy, but gets to the point. SST13. So this is where we're going to test the stepper motor interface. Okay. Okay. Flash the assembly with the. Okay, so what we're going to need to do is we're going to fix all that. We're going to do firmware, basic modules, folder, stepper test. Very original, I know it. I know it. With the test firmware. Okay. That the bench top I set to DC and is set to at least 2 amps. We want to make sure it's at least able to deliver 2 amps because remember the stepper motor is driven straight by the power supply, the 24 volt input. It's not going to be powered by any of the 3.3 or the 5 volt power supply on the board. So you have to make that as set at least 2 amps. All right. Connect. So I'm going to have a stepper motor already also rigged up properly, wired up properly to one of the terminals, one of the pluggable connectors. I've got one with a relatively, long kind of lead on it. I'll be able to just pre-wire into a terminal block. That way we just kind of plug, pluggable, so we just plug it in. Connect a 4-wire bipolar, my bad. Bipolar to the CN. Oh yeah, we still need to test the fan too. We'll get to that. We'll get to that as well. We'll test the fan, the temperature sensor, but I'm kind of interested also in getting the making sure this works too right here. And my brain just went dead. CN7 to the assembly. So, with the so the color code, I don't have it with me. What do I? Is it written down on this notepad? Please be on this notepad. If it's not, I'll have to dig it up and I think I've got the color code written down on another from my stepper motors, but so the stepper motor basically has a motor A put to CN7. All right. I'm just going to move this off the screen so I have to keep. All right. CN7, terminal 1. To okay. 2. See, that is going to be terminal 4. And the V minus CN7 3. All right. Let's go and ditch this. Before I get too far ahead, do we have create 4-wire appropriate 4-wire bipolar stepper motor. Again, I'm going to have this pre-wired so you don't have to worry about it. Just remember your A and B, right here, I wanted them to be straight shots rather than try to do vias or anything in the board where I could avoid it. I just wanted them straight shot to avoid any kind of power loss or anything. So that's why they're wired this way, and I didn't kind of cross. So output 1's here and output 2's here. And you have to refer to the proper input identification. Now, a lot of them seem to carry the same, I think, red, black, blue, green for the wire colors, but I have seen different ones out there in the wild. So you always want to refer to the documentation for that stepper motor. Most of the time what would happen is you just wouldn't get motion. It wouldn't move. You sometimes just hear it hum, make that really loud whiny sound. That's a lot of times what you're going to run into. If you miswire it, it just won't go. So this, we've got that, got that, stepper test firmware. That's how power supply is with all right. Disable the then effect. Okay, so we want to turn off the power supply because we don't want any, have to worry about an input or anything. We want just basically a raw test. So basically, as soon as you turn it on, the stepper motors just start turning. I think I'll have it kind of rotate, one direction for a couple of seconds and rotate the other direction. So what we'll do is we'll take like a piece of tape or something and put like a little flag on the output shaft. Ooh, pardon me. Put a flag on the output shaft so you can watch it rotate. Or we'll even kind of build something, something to hold the stepper motor. We'll think about it. Definitely may want to do something like that for like a test jig for production testing. We'll see. We'll see about all that. But that's a future problem for when we get the board and we're getting closer to release. That way we can write the production test plan and maybe build and design an actual test fixture. That way we can simplify this process so we're not jumping through hoops every time to test each board that needs to go out. Because my goal with this project is to, push it, get it out there, maybe even advertise it, and sell it to help support, the channel and what my hobbies and what I like doing. Because I have plenty more plans, and there's other videos I've already kind of started recording that I'm going to launch in January for 3 more series that kind of revolve around the same project, but different parts of it. Because I feel like what I wanted to accomplish with this video series turned into more of the design and less of the project management / quality management stuff that I really wanted to focus on too. Because I'm a designer. I like designing and building. Paperwork's not the thing I really enjoy doing, but it needs to be done. And I think for this project, I definitely want to keep as much, put as much into it for documentation and stuff. But we're going to do for the next project that I'm going to be doing, that we're going to be launching. It's going to be more, each video is going to be more intensive. Each series is going to be more intensive of the documentation that goes along with that project, as well as an overall QMS building for the Magic Forge. So it's not going to be a what if scenario for all of it. It's going to be, this is what I want to do for what I'm doing on this side. Actually set myself with, for success for the future. But I'm hoping that I'm covering enough of what I think is important with this series that it helps anybody looking to do this understand what they're walking into. You should definitely have test plans like this. You should know what, you should have everything tested, documented before you even consider shipping a product out to the market. That way, that way you can answer any questions people have. If you run into issues in the field, and you can make advertising material or flyers or whatever, however you want to do it, and it's all truthful information, stuff you've validated, you've already tested, it works. So you might even drop the voltage down to 12 volts for this device, because the stepper motor, driver, and all this should even operate at 12 volts. We'll test it. We'll even kind of push the power supply up a little higher, because the power supply chips, let's see here, the regulators, they're supposed to handle up to 32 volts. My power supply only goes up to 30. And I think the stepper driver can handle up to 48 volts. So we'll push it. We'll push it to the 30 volt limit. We'll see what happens. Obviously, I want to do that, to do an over voltage test, and things like that might be destructive, but we'll watch what happens. But that'll come again after we've done the initial testing and we validated that this design does work. And then we're going to build up another board and do destructive testing. We're going to push it to its limits. We're going to short stuff out. We're going to see how it handles under heat, under pressure. See what fails, what doesn't. Now there's another thing we can do. We're running low on time, so again, I'm going to keep these videos around an hour, unless we're really too deep into something to stop right then and there. As far as the testing goes, the general bench testing. Well, let's figure this out. Okay. Let me finish this out first before I get ahead of myself. That's a bad habit I have. Enable the output and the motor. It should rotate clockwise. I'm going to do something that should rotate clockwise for – Let's just be simple about it. So let's say 30 seconds. Then stop and start and start. Clock wide. Okay, so that's what it should do. When you enable the power supply, the ESP32 should boot and should start driving the stepper motor in this pattern. I'm not really gonna worry about speed. It's just gonna go however it goes. I've been doing some testing with the LED PWM firmware, and it doesn't really do what I want it to do for stepper motor control. So I think we're gonna have to. I'm gonna have to actually, for constant speed at a relatively slow speed, it's fine. But if you want something at a higher clock rate, I'm gonna have to actually find firmware that we can generate higher clock cycles, basically higher pulses. So I'll do some digging, and I'll probably end up having to write a sub module, like a header C source file for the actual dev kit when I go to launch it. So that's what I'll be doing for that. But for this, it's just gonna be a basic rotate clockwise, stop, rotate counterclockwise, stop, and then repeat the cycle. If this is observed, the test is a success. So that's SST 13. 13 does the stepper motor driver IC properly. Because I'm always have to update the firmware too, make sure the firmware is written for this, because let's go back here. So not only do I have that, but there's some other things that we're going to need to kind of test for and figure out how to test for, but we also have the microstepping. So the ESP32 will be able to control the microstepping via lows or highs. So I have to make sure all that's in the firmware, reset, enable, all this is all set right. So I have to do all that setup in the firmware and get all that working right. So we'll go for that. So that should do that. That should run that. I have a PLC program to write and do some basic testing with. There's other tests we need to derive or devise, because we still need to test the temperature sensor input and the fan. So what I'm going to do, so I might, okay. So for these two tests, they might be a little bit more complicated, and that might be a good thing that we're leaving them down at the bottom near the end. Because for these, we might actually use the UART console for, which is great because I can show you how to interface it with like the fan. We'll use the UART console, so basically we'll have a subroutine just to read the temperature sensor. We'll have 2 extra thermometers. I've got like a generic desktop thermometer that I got off Amazon that shows temperature and relative humidity. I just keep that way. I know how much I'm roasting or freezing in my workshop in the basement. Currently it's 23 degrees Celsius in my office, and I run hot anyway, so it's a little warm for me, but that's fine. But I also have my Agilent. I have an Agilent multimeter that has thermocouple inputs, and I'll be tying one of those thermocouples. So I'm going to probably be writing the test to also display this, the PCB. So what we'll probably do is be tying a thermocouple close to this guy. So they should be reading about the same temperature. So I have a thermocouple here. We should be able to read that, read the thermocouple on the meter and compare. And then obviously I'll get the temperature for the room. It'll be ambient. I know it won't tell us like what the board temperature is or relatively close, because this IC, the temperature sensor, will definitely pick up the board temp, especially as this guy starts driving, starts putting that heat down to the ground plane. This guy will pick up on that. So this guy, the way I've got this guy plugged in there, having an actual heat sink may not be necessary, but I'm still going to stick one to the guy. Just going to show you in case you've never worked with them. Actually, I'll just go to Amazon. I'll just kind of show you. Yeah, here we go. I think I've got a set of these. If not, I'll be ordering a set of them. Basically, these little guys. You know, these little guys. I'll get the measurements. I'll find the one that'll actually work. So it's basically got the permanent, mostly permanent. I'll say that. I mean, it's mostly permanent as long as you don't fidget with it too much. So basically a little miniature heatsink that will just stick on top of the stepper driver, and then the fan will help augment it and blow, help kind of keep it cool. Because if you're going to throw this in an enclosure, because we are going to design and print an enclosure, and maybe you'll be part of that process using Fusion to do, and I'll 3D print it. Who knows? I might even pick up some ABS filament to print it out of because it's more heat tolerant. Because currently I pretty much predominate everything with PLA and PETG, but maybe I'll pick up a spool of ABS just for printing an enclosure with this. And so we'll see from there. We'll go from there. But yeah, I'll probably order some of these. Like I said, I gotta get dimensions, see what size would fit better. I just snowballed it, or just, spitballed it just to, get an idea. That way you know what I'm talking about. But I'll order a set of those. Long term, if I do use those, I'll probably film with a bomb and get them through a source, a long-term source such as Mauser for actual production run. So that's something we'll have to add to the bomb, is a heat sink for this guy. But we may not need it, but I don't like to take things to chance. If I could spend, 20 cents on a heat sink along with a fan to preserve the life of this chip, which will extend the life of this product, I'll do it. It's worth it to me. I don't like playing those games, and I like to plan for long-term availability and viability rather than planned obsolescence. So if I can throw a heat sink on there along with a fan, and, I may have to charge a little bit more for it, but I'm going to do my best to guarantee the product's going to last longer. Because you got to consider, we've got a big, kind of this big ground pour right here, this big copper pour tying the ground. Then it's going down to a full layer inside the PCB of nothing but a ground plane. It's a huge ground plane. I don't know what color we're at. I can't remember what color it is. I think it's that color. Yep. So that one, layer 4. So it's going to be by the bottom layer. So that is one. The whole thing is ground. So that whole thing's going to act like a heat sink. So it's going to help pull heat through those vias down into that plane. And then it's got another pad on the bottom, a little pad that is tied into. That's going to be another heat sink on the bottom. So we've got all this thermal mass that's going to help pull heat away from this guy, along with a fan. So I don't think this guy overheating is going to be a problem. Although we will test for that. We'll use a heat gun, and we'll just see. We'll see how far we can push it. I mean, if we smoke a board or smoke some parts, we will. That's part of the testing process. Called destructive testing. But again, we'll just give up a board for it, and that's fine. That's the cost of doing business. You have to sometimes spend money and break some stuff in order to. And then I also want to mention I made another mistake, and it's my fault. My complete fault. Not that I own it. I also realized that I was looking at the design files, looking at specifications, and yeah, I wanted 2-ounce copper top and bottom, but I didn't make my PCB traces thick enough for 2-ounce copper. So I have to go through, update my design rules, go through every one of these traces and make them bigger to account for 2-ounce copper. That was my fault, my mistake. I wasn't even thinking about it because I usually use just 1-ounce copper or less. Typically just 1 ounce for your top and bottom layers. Inner layers can be half an ounce or greater. But your PCB trace width and spacing, there are standards, there are minimum sizes and standards for dealing with the different copper thicknesses. So this is my bad. I own that. I just realized I'd made that mistake. I completely forgot about that. That I wanted 2 ounce copper and I didn't make some of these, like these guys are thick enough, but it's the regular data signal lines, these guys that aren't thick enough. So I'm going to have to go through and clean all that. That'll be on the next board spin. We'll worry about that if we revise the board or anything, because I might revise it anyway to throw test points. We still have plenty of room in here around the stepper driver to throw a couple more of these test points. We can shove a couple in there. We still have plenty of layers, signal layers, to throw more data through, shuffle a couple of these inner traces around and be able to do that. So we'll probably spin this board anyway again to account for that, the new test points to tie into the stepper driver, so we can get some of those signals that we've identified here. So we can just test point them. And then we'll update the test plan for it, because there'll be another first article for basically revision 2, Rev 2 of the board. So, we'll go from there. So one thing about engineering, man, it's easy to make mistakes and overlook stuff when you want to go. And being a team of just one person does make it a little bit easier to make mistakes. I don't have somebody else to double check my work. And I have to kind of, eyeball it and go as best as I can on my own. Without a team to properly, hey, look, you made a mistake. Your traces aren't wide enough, or you forgot you're going to get 2 ounce copper rather than 1 ounce copper. So they're mistakes. They happen. Don't beat yourself up over it. Just realize you made them and correct them for the next rev. But 1 ounce copper should hold this, especially with as beefy as these traces are, and the ground plane, the power, the heat sinking that we're going to be throwing on that, because a lot of it, most of this is logic. Is the 2 ounce copper really isn't for logic. It's mainly for this. We may not need 2 ounce copper. I'm going to double check, because if they're accounted for like thinner traces, this may be more than enough. I will double check. And I think a lot of it's for the heat sinking of this guy, but we're going to give this guy proper heat sinking, so I don't even think that's going to be a problem. But yeah, so the other tests use the UART interface serial console to test the fan, because we'll be able to read the tach. We'll be able to send out PWM signals, watch the fan go, control its speed and watch its speed, read this guy, compare and all that, and kind of figure out what to do with the data coming off of that. Because we could, that's pretty much, I kind of wanted to throw that in there. Was it necessary? No, but I think it's a helpful feature, especially if you've got this in an enclosure. It can help detect problems early and report back. If you've got this in an enclosure, or maybe in a cabinet, or you're doing some kind of robotic device with it, you're controlling a stepper motor or something, whatever. That way you at least have another piece of data you can pull off it, which is the temperature of the enclosure PCB. And that would help you diagnose anything, like if you get a fail condition coming from the fault. So remember, when there's no fault, this will be high, 3 volt. But any fault that causes this thing to reset or shut down will be seen as a low. So it doesn't mean you can't interpret it. It's not like there's going to be like a pattern, like a high, low, high, low, high, low pattern, like a binary pattern. It's either going to be 3 volts for no fault, or ground, a low for, hey, there's a fault. I can't tell you what it is, but there's something wrong with me. So that's what that'll be for. That way you can use that as you can set that up on like a ISR or something to help just at least monitor, make sure this guy. Some of these other inputs we could have set up, but we didn't. Like the home, I can't remember what that does, but it really wasn't too super useful, because kind of reset kind of does something similar. So yeah, we might want to revision 2, throw in test points for that. So yeah, tomorrow, which is Saturday, let me double check. Holidays always screw me up. So yeah, tomorrow, Saturday, 2 p.m. we'll stream. We'll start kind of capturing the test and to get the plan for the fan and the temperature sensor. I've already got like a fan on another project that does this exact same thing, another PWM tack fan that I've already got firmware I wrote. And it could be along with the UART interface. I can kind of show you how to kind of get those together and get those kind of pulled together. Even though we won't have a fan to test, but I can at least show you the firmware. So right here, this is done. This is good. We'll in a good place. We'll leave that. And this is in a good place. We'll leave that. And I'm going to end the video here. Thanks for catching us out. Sorry for rambling, going on about things, but that's just how I operate. I like to go on tangents. I really appreciate you sticking with us this long. It's been fun. And it's definitely been a learning experience for me as well. So I thank you. I thank everybody who's been checking out the series, checking out the Twitch streams, interacting, and leaving comments on YouTube. I really appreciate it. I try to read everything possible and respond when I can to the comments and stuff. So have a good rest of your evening and see you tomorrow.